Hello everyone, I hope you are doing well. In this video, I want to do a review for exam 1. In this video, I'm going to go over the concept of limits and derivatives, and later on in the video, I'm going to go over the practice exam that I sent out last week. All right, so let me quickly go over what we have learned so far in this course, like the big picture and then the details of each concept that we have learned. All right, so at the beginning of the semester, we learned that we start the course with slope of a secant line, or the slope of a line passing to 2 points, right? And also we use a formula to calculate the average velocity or average rate of change between two time periods, right? And the formula that we use has the form. So this is the slope equal to y2 minus y1 over x2 minus x1. You can swap y2 and y1 and using the notation f of x2 and f of x1 as follows. So f of x2 minus f of x1 over x2 minus x1. And again, this particular formula can be used to calculate the slope of a secant line, or the slope of the line passing through 2 points x1 comma y1 and x2 comma y2. And again, you can swap y2 by f of x2 and y1 by f of x1, and it's going to carry the same meaning. All right. And also you can use this formula to calculate the average velocity or average rate of change of an object moving between two time periods. Okay. Now, from this concept of the slope, the secant line, or average velocity, we say that we can take the limiting value of the slope of the secant line to obtain the slope of the tangent line, right? And we can take the limiting value of the average velocity to obtain the value of instantaneous velocity or instantaneous rate of change. And the way to do that is to you can calculate now the slope of the tangent line. That is, take the limit of x2 approaches x1 of f of x2 minus f of x1 over x2 minus x1. Okay, so that's what we did, right? And we want to put this formula in a more general form, right? And to do that, what we did is we swap out x2 and replace that by a variable x, right? So this formula becomes limit of f of x minus f of x1 divided by x minus x1 at x approaches x1. Okay. And of course, like as I mentioned, we want to have this as a general formula. So we continue swapping things around, just replace one letter with another letter. So that in this case, instead of x1, I'm going to use a. So x1 become a. And this is the formula for you to calculate the slope of the tangent line at the point x equal to a, or the instantaneous velocity, right, at the instant of x equal to a. Right? So this is the slope of the tangent line to the curve y equal to f of x at x equal to a, or you can do this, use this formula to calculate the instantaneous velocity at a point at x equal to a. All right. In using this formula, we can do this, right? We can find the slope of the tangent line or instantaneous velocity. And the formula or the notations, right? The notations that we usually use is f prime of a. Right? So that is the derivative as a rate of change, or derivative at the slope of the tangent line, or the derivative as the instantaneous velocity. In a more general form for the derivative is for us to actually rewrite this particular formula in the following manner, right? So instead of writing the limit of f of x minus f of a over x minus a as x approaches a, what we do is that we let h equal to x minus a, right? So the distance between the point x and the point a. And therefore, you can also write x as a plus h. Okay. So the formula, this formula now becomes, right, that prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a over over h. Right. So again, this formula is still used to calculate the derivative of functions at a point, right? Or more specifically, the slope of the tangent line to a curve at a point, or instantaneous velocity at x equal to a. Okay, this is still the derivative of a function at a point. What about the derivative of a function in general? So what we did is that we take out the a, right, or we vary a, or replace a by a variable x. So in this case, what we do is that if we let, or we vary a, or replace a by a variable x, we get, so we get the following formula: f prime of x equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Right. So this formula is called the limit definitions of the derivative. Right. So this is limit definitions of the derivative of f. Okay. And of course, we can find this the derivative provided that the limits exist. So provided that the limit exists. Okay. So that's the big picture of what we have covered so far in this course. Now, later on, we're going to go over a little bit more details of whatever related to limit and derivatives. But for now, right, so to find the limit of the function, you can use the definitions of the limit. Or if you want to find the derivative of a function at a point, you can use this particular formula. All right, so now let me go into details of each concept that we have covered so far in the course. So the first concept is for limit of functions. Right, to find limit of a function, you can actually use the limit laws that there are a few different limit laws that we have learned so far, right? But the most widely used laws for the most widely used limit laws that get applied in the course is direct substitutions. Right? So we can just use direct substitutions to calculate the limit of the functions. However, as we have done up to this point, most of the times we don't have the luxury just directly use direct substitutions and get the result. When we use direct substitution, the limits sometimes lead to an indeterminate form of 0/0, right? So may lead to an indeterminate form zero over zero. And to avoid this indeterminate form, what you can do is that you can reduce the functions that you want to find the limit by factoring, right? You can factor the numerator or denominator, or you can reduce the functions by conjugating method, right? So this particular method is used when you have a square root function involved in the numerator or in the denominator, right? You can also calculate the limit of the functions using the squeeze theorem, right? And we went over a couple of examples in class related to sine and cosine functions. All right, and in the homework, in web work, you also done some problem related to squeeze theorem. Okay, now there's a very important theorem for finding the limit of a function is the existence of limits, right? So the limit exists if and only if the left-hand limit equal to the right-hand limit and equal to the same value. Right? So the existence theorem, the existence of limits, right? So the limit of the functions f of x as x approaches a equal to L mean exist, right? So let me exist if and only if the left hand limit, so limit of the function as x approaches a from the left equal to the limit of the functions as x approaches a from the right equal exists and equal to the same value. Right, so that is the existence of the limits, right? And you have to be very careful when you find the limit of the function, especially for the limit of the piecewise defined functions. We're gonna go over a couple of example or a couple of problems in the practice exam related to the existence of limits. All right. Now, moving on from the limit of the functions, we have continuous functions. So most of the time, we are allowed to use direct substitution in finding the limit of the function at the point A, because the functions of the considerations are continuous, right? And to have a continuous function at a point, so the function, so a function is continuous at a point A, require three things, or right. So the first one is that f of A is defined, right? Or the evaluations of the function at A is defined, or A is in the domain of the function f. So A is in the domain of f. The second condition is that the limit of the function as x approaches A exists, right? So we see this concept a little bit earlier up here, that the limit exists if and only if the left-hand limit equal to the right-hand limit equal to the same value, or the one-sided limit equal to one another. And the third condition is that the value of the limit as x approaches A equal to f of A, or equal to the evaluation of the function at A, or the output of the function at A. So when you have these three conditions satisfied, you can say that the function is continuous at a point of considerations. All right. Sometimes you don't have continuous functions, or the function is discontinuous at certain point. And there are three types of discontinuities that you need to classify when you see one. All right. So three types of discontinuity. Right. So the first one is called the removable discontinuity. So you classify this when you see a hole on the graph of functions, but the limits still exist. Right. The limit as the point of consideration still exists. Right. The second type of discontinuity is called the jump discontinuity. In this case, you also see holes on the graph of the function, but the limit does not exist. Okay, and the last type of discontinuity is called infinite discontinuity. Okay, so where the limit on the left go to either negative infinity or positive infinity, or the limit from the right go to either negative infinity or positive infinity, then you have infinite discontinuity. Right. So here's the following graph for us to help us understand the removable discontinuity, jump discontinuity, and infinite discontinuity. All right, so for the first two pictures here, you can see these two are the type of discontinuity or removable discontinuity, because you see holes on the graph of the function, but the limits still exist, right? So the limit from the left equal to the left-hand limit equal to the right-hand limit equal to the same value. Similar in this case, this is also a removable discontinuity. So let me quickly note that this is removable. So this is also removable discontinuity. In this case, this is called the jump discontinuity because you see holes on the graph of the function. So the function is discontinuous at x equal to 0, x equal to 1, x equal to 2, x equal to 3, so on and so forth. And it's classified as jump discontinuities because the left-hand limit does not equal to the right-hand limit. And so we call this a jump discontinuity. And for the last picture here, you have infinite discontinuity because the limit as x approaches a from the left, sorry, x approaches 0 from the left go to positive infinity, and the value of the limit as x approaches 0 from the right also approaches infinity. So therefore, you classify this one as infinite discontinuity. All right. So we start with continuous functions and we move on to limit at infinity. Right. So let me quickly point out that for infinite discontinuity, when you classify one as such, you can actually identify vertical asymptote from this analysis. So vertical asymptote. And we call this infinite limits, right, to help us find vertical asymptotes. So in this case, in this particular example, x equal to 0 is a vertical asymptote of the function. Now we move on to limit at infinity, right? So to find the limit at infinity, what you do is you calculate the limit of the function as x approaches negative infinity. and hopefully give you some value. And you find the limit of the functions as x approaches positive infinity. Hopefully it gives you some value, right? Calculate the limit at infinity, or when you find the limit of the function as x approaches either negative infinity or positive infinity. This helps you determine the end behavior of the functions. So determine the end behavior of the function. Right. So meaning that what happened when you let x, what happened to the functions when you let x to negative infinity, what happened to the function when you let x go to positive infinity. And by doing this, you can also identify horizontal asymptote of functions. Okay. So that's limit at infinity, right? So help you to identify the end behavior of the functions, or help you identify horizontal asymptote of the functions. All right, so we move on to, right, so you have the limits, you have the definitions, limit definitions of derivative, and so you can find the derivative using the limit definitions, or you can find the derivative using some basic differentiation rules. So we have basic differentiation rule. Right. So there are different rules that we went over in class. So the first rule is that the derivative of a constant, right? So if you have f of x is a constant function, c, right? So then f prime of x is going to be equal to 0 because the slope of any constant function is 0, right? Or the slope of a horizontal line is equal to 0. Therefore, the derivative of constant is equal to 0. We have learned about power rule, that if you have a function of the form f of x equal to x to the power n, then the derivative is that of n times x to the n minus 1, right? Basically, you take the exponent n, you bring it to become multiplications, and you subtract 1 from the exponent. In this case, you can choose any value of n, right? So any value of n should work here. So a few notice for using power rule is that when you see a root function, you can turn that into a power function. It's going to be a lot easier for you to find the derivative. Or when you see a reciprocal function, you can turn that into a power function as well. It's very helpful to finding the derivative, right? So when you have root function, can turn that into a power function. A few common root functions that you may see in the course so far is the square root function. You can turn this into x to the power 1/2 function. So that's the power functions. You have a q root functions. You can turn that into x to the power 1/3. Or more generally, if you have a root function of the form, this is m of x to the power n, right? M root of x to the power n, you can turn this into x to the power n divided by m. So this is called the rational exponent. Okay. Or you can have a reciprocal function of the form 1 over square root of x. You can turn this into a x to the power negative 1/2, right? Again, doing this allow you to find the derivative of the functions a lot easier, a lot faster. Okay, and then we move on to something called the constant multiple rule. So constant multiple rule. Now, if you have f of x equal to c times g of x, right? So in this case, f of x is a scale function of g of x. So when you find the derivative of f, what you do is you basically take the derivative of g and then scale the derivative of g later. So that's the idea. You have sum and difference rules. Right. So derivative of the sum is the sum of derivative. So f of x plus g of x prime is equal to f prime of x plus g prime of x. Similarly, for the case of derivative of a difference, right? The derivative of a difference is difference of derivatives. So hopefully that should be straight forward for us. You can also, so there's another rules. There are two more rules that we learned up to this point is product rule and quotient rules. So product rule and quotient rule. So derivative of a product, so for product rule, you have u times v prime is equal to u prime times v plus u times v prime. And for quotient rule, you have u over v prime equal to u prime times v minus u times v prime divided by v squared. And one conditions that we need to impose is that v function v has to be different from 0. We don't want 0 in the denominator. One of the practical applications of derivative that we went over in class is to find the derivative and set that equal to 0. So the idea is to find a point on the curve at which the tangent line is horizontal, and it's very useful for us down the road when we learn about finding maximum and minimum of functions. So one applications we can use is find a point on the curve at which the tangent line is horizontal. So that is what you do is you find the derivative of the function and set that equal to 0 and you solve the value of x. Right? So in this case, what I mean is you set y prime equal to 0 or f prime of x equal to 0, and then you solve for x. Okay. So basically, that's what you can use to find the derivative of the functions. So again, to find the derivative of the function, you can either use the limit definitions of the derivative, or you can use basic differentiation rules, or the two rules that we just learned about is product rule or quotient rule. If you have product, you have a quotient. Okay. More into derivative of a functions or differentiations or differentiable function. So the definition for differentiable function is that a function f of x is differentiable at a if f prime, if f prime of a exists. Okay, so f prime of a exists. Now we go back to the limit definitions of derivative, right? So f prime of a exists, meaning that the limits of, so let me go back up here. So if prime of a exists, that means the limit, this limit has to exist, right? So that means the left-hand limit equal to the right-hand limit equal to the same value. But most of the time, the functions that we consider a continuous function or are differentiable functions. So very easy to find the derivative of such function. Okay. More important theorem that we consider in the lecture related to differentiable function is that differentiability implies continuity. So differentiability implies continuity. So if a function is differentiable at a number a, then the function is continuous. So this is just a one direction statement, right? So if a function is differentiable at the number a, then the function is continuous at a. However, the reverse direction is not always true, right? That is, if the function is continuous at a, there's no guarantee that the function is also differentiable at that point. All right. And we will see in the following cases, right? Sometimes the function is continuous, but the function is not differentiable. So functions failed to be differentiable. Right. So there are three cases where the functions fail to be differentiable. The first one is when the function has a corner or a kin. The function fails to be differentiable where there's a discontinuity, right? And the functions fails to be differentiable when there is a vertical tangent line. Okay, so I'm gonna show you three different graphs to illustrate the three cases where the function fails to be differentiable. All right. So first, in this case, there's a kin or a corner, so the function fails to be differentiable. So there's a discontinuity. So in this case, the function fails to be differentiable as well. And where there's a vertical tangent line, in this case, the function fails to be differentiable. All right. So that's it for the materials for exam one, right? So we cover all the materials up to product rule and quotient rule and differentiable functions. The next part of the video is where I'm going to go over the practice exam. Okay. And of course, let me know if you have any questions. So for exam one, there are multiple parts to the exam. There will be true false questions, multiple choice questions, short answers, and also the written responses. So as I mentioned in class, if you study, go back to the lecture note, go over the lecture note and try to do the practice exam, you should do fine for the actual exam. So without further ado, let me go over the exam together with you here. So the first part is the true false question part. So let me go over one question at a time. So in the first questions, if the limit exists, then the left-hand limit and the right-hand limit both exist. So these questions relate back to the existence of limits theorem, that if the limit exists, then the one-sided limit has to exist and has to equal to the same value. So therefore, it is the two questions, two answer. Now, for the second questions, if the limit does not exist, then the limit from the left and the limit from the right do not exist. This is not true though, so this should be a false statement. What I mean by that is the limits do, the left hand limits do exist and the right hand limits do exist, but they do not equal to one another. So the limit may does not exist, right? So for example, if you consider the following function, right? So you have this function and you have this part of the function, right? So the left hand limit exists, the right hand limit exists, but they do not equal to the same value. So therefore the limit at the point of consideration does not exist. So therefore this is a false statement. The third question is if f and g are differentiable, then the limit of the sum, the derivative of the sum is equal to the sum of derivatives. So this is a true statement. The next questions, if f and g are differentiable, then the derivative of a product equal to f prime times g prime, which is incorrect. Right? So it should be a false statement. Right? So the derivative of a product, so f times g of prime is equal to f prime times g plus f times g prime. All right, so the next question, if f is continuous at a, then f is differentiable at a. Not always, right? So it should be a false statement, right? So we have the, go back to the review, right? So we have cases where f can be akin. So when f is akin, then f is continuous, but it's not really differentiable. Right? So when you have the vertical tangent line at the point of considerations, the function is still continuous, but it's not differentiable at that point, right? So this should be a false statement. Now, next, the last question, if a function is not differentiable, and then it cannot be continuous. Right? So this question is kind of a negate of this statement, right, of the above statement, that a function is not differentiable at x equal to c, then it cannot be continuous at x equal to c. That's not true all the time, because what we just mentioned about is that the function has a vertical tangent line, right? So it's continuous, but it's not differentiable. So it is a false statement as well. Right. Moving on to multiple choices questions. So in the first question here, if you use direct substitution, you will see that we have a indeterminate form of the form 0 over 0. So to get rid of this form, what you can do is that you can simplify, or you can factor the numerator in the following manner. So you can take the limit of x squared minus 4 over x minus 2 as x approaches 2. All right, so the numerator, you can apply difference of 2 squared. You can get x minus 2 times x plus 2 over x minus 2. Right, now you can cancel out x minus 2 and you're left with limit as x approaches 2 of x plus 2. At this point, you can just use direct substitution by letting x equal to 0, x equal to 2. You get 2 plus 2 equal to 4. So the answer should be B. The limit of this function is equal to 4. Now moving on to the next problem. So here you have a piecewise defined function, and you have to be careful when you're having the absolute value part in your function of considerations. Now, the question is to find the limit of the function as x approaches 3 from the left. Now, let's analyze this problem a little bit, especially the part where you have an absolute value. So for x absolute value of x minus 3, there is 2 parts of this one. So this is the piecewise defined functions. So you have the positive x minus 3 if x is greater than 3. Now, let's not consider the equal sign because you have a denominator x minus 3, right? So when x equal to 3, the function does not exist, right? So let's not consider the equal part. Now you have a negative x minus 3 if x is less than 3. Okay, so this is the piecewise defined functions. Now you already consider the numerator. Now combined with the denominator, that is the absolute value of x minus 3 over x minus 3. And then you get x minus 3 over x minus 3 if x is greater than 3, and negative of x minus 3 over x minus 3 if x is less than 3, or this should be equal to positive 1 if x is greater than 3, and is negative 1 if x is less than 3. Okay, so there are two parts to this function. The function is equal to positive 1 when x is greater than 3, and the function is equal to negative 1 when x is less than 3. Now, when you find the limit of the function as x approaches 3 from the left, that means you want to consider the part of the function when x is less than 3. So that is the limit of absolute value of x minus 3 over x minus 3 as x approaches 3 from the left equal to the limit of negative 1 as x approaches 3 from the left. Right, so it's just equal to negative 1. So the answer should be B, negative 1. Now moving on to the third problem. This is also a piecewise defined function, and you want to find the limit of the function as x approaches 2 from the left. So x approaches 2 from the left, that means you want to consider the function, the part where x is less than 2, so this part. So you want to do limit of the functions as x approaches 2 from the left, or finding the limit of 1 plus x squared as x approaches 2 from the left. Now you just use direct substitution. That is 1 plus 2 squared equal to 1 plus 4 equal to 5. So the answer should be A. Okay. Now moving on to number 4. So number 4 asks you to find the limit of the function as t equal to 1. Now again, this function is a piecewise defined function, so you need to consider the left-hand limit and the right-hand limit. So the left-hand limit is, so the limits of the function f of t as t approaches 1 from the left. So t approaches 1 from the left, that means you want to consider the part where t is less than 1. So the limit of negative t as t approaches 1 from the left. So this is negative 1. All right. Now, the limit of the functions as t approaches 1 from the right, that means you want to consider the part where t is greater than 1. All right. So limit of t squared as t approaches 1 from the right, or 1 squared equal to positive 1. So the left-hand limit does not equal to the right-hand limit, right? Therefore, you can say that the limit of this function does not exist, or this should be choice C. Now, moving on to number 5, this is where you need to find the infinite limit at infinity, right? So the concept for this is to look at the highest exponent on the numerator and the highest exponent in the denominator, and you take out the part when you have the highest exponent. So what you do is that, so on the numerator, the highest exponent is 4, so you take out x to the power 4 as a common factor, and you're left with 1 plus 1 over x square plus 13 over x to the 4th divided by the denominator. The highest exponent in the denominator is 3, so you take x to the 3rd power as the common factor. You get x cubed times 1 plus 8 over x squared plus 9 over x to the third power. And again, you want to find the limit at infinity as x go to positive infinity. Now you can see that you can cancel out x to the 4 and x to the third, or simplify x to the 4 and x to the third power, and you're left with limit as x approaches infinity of x time 1 plus 1 over x squared plus 13 over x to the fourth divided by 1 plus 8 over x squared plus 9 over x cubed. Now, so when x approaches to infinity, this term approaches 0, this term approaches 0, right? As well as this term and this term. Okay, and you're left with just limit as x approaches infinity of x. Right, so and by direct substitution, quote unquote, right, you get infinity, or you say that the limit does not exist in this case as well. All right, so moving on to short answer. Given this following graph, you need to identify the following. So first, part A, you want to find the limit of the following point, right? What happened to the limit of the function as x approaches -4 from the left? There's no clear number here, but in the test, in the actual test, I will give a picture with the explicit number for us to identify. All right, so approximately I can say that at this point, the limit of the function as x2 approaches -4 from the left is equal to +1. All right. And a limit of the function as x approaches -4 from the right is equal to -1. Right? So the left-hand limit does not equal to the right-hand limit. Therefore, the limit of the function as x approaches -4 does not exist. Now, the limit of the function as x approaches 2 from the left is equal to +infinity. And the limit of the function as x approaches 2 from the right is also equal to +infinity. And therefore, you can conclude that the vertical asymptote of the function is x equal to 2. All right. Now, by looking at this graph, you also need to identify and classify the discontinuity. So the function is discontinuous as the following point. So the function is discontinuous at x equal to -4 and x equal to 2. Right? So x equal to -4 and x equal to 2. At x equal to -4, this is the jump discontinuity because you see holes at the point of consideration and the limit does not exist. So this is a jump discontinuity. At x equal to 2, you can see this is infinite discontinuity because the limit will lead to +infinity or -infinity in some cases. So this is called infinite discontinuity. Now, the next part is to determine and classify the point at which the function is not differentiable. Right? So the function is not differentiable at x equal to -4, at x equal to -1, and at x equal to 2 and at x equal to 5. Okay, so there are 4 points at which the function is not differentiable. So the function is not differentiable at x equal to -4, x equal to -1, x equal to 2, and x equal to 5. Now we have to classify this this point where the function is not differentiable. So as x equal to -4, you have this continuity. At x equal to -1, right? So this is a kin, right? Therefore, it's not differentiable. Kin corner. At x equal to 2, this is infinite discontinuity, so you can classify as discontinuity. And at x equal to 5, as you can see here, this is a vertical tangent line. So you see, this is vertical tangent line. So that's it for the short answer. Now moving on to the written response questions. The first problem here is that you want to find the derivative of a function using the limit definitions of derivative, right? And the formula that we're going to use to find the derivative of the function is that of f prime of x equal to the limit of f of x plus h minus f of x over h as h approaches 0. Okay, so that's the formula that we're going to use to find the derivative of the functions f of x equal to 2x plus 1. So f prime of x is going to be equal to limit as h approaches 0 of f of x plus h, that is 2 times x plus h plus 1. So this is just the part of f of x plus h. Now we do minus f of x. So minus f of x, that is minus 2x plus 1 in the parenthesis, because you have the negative in front of it. Now to get all together divided by h. If you use direct substitution at this step, you will find out that we have the indeterminate form of 0 over 0. So we need to avoid that, or we need to eliminate that form. So what you do is you expand the numerator and combine like term or cancel out where you can find some cancellations. So here the limit as h approaches 0 of 2x plus 2h. So what I did is I distribute 2 into the parentheses plus 1. And then over here, I distribute the negative into the parentheses. Remember, when you have a negative in front of parentheses, with addition and subtractions, the negative will go to all the terms inside the parentheses. So that is negative 2x minus 1 altogether over h. Now you see that, let me use this color. So 2x and negative 2x cancel out, positive 1 and negative 1 cancel out, and you're left with just, so limit as h approaches 0 of 2h over h. And you can cancel out the h. You get limits of 2 as h approaches 0. So this is equal to 2. So the derivative of this function is equal to 2. And for if we already familiar with basic differentiation rules, you can automatically see that the derivative is equal to 2. But the requirement for this particular problem is to use the definitions of the derivative. Okay. Moving on to the next problem. So in class, we cover the Chris theorem, right? And we, more specifically, we want to focus on function related to sine and cosine. So to find the limit of this function, we need to use this Chris theorem. And the Chris theorem can be done by first consider a function cosine of 1 over x squared. All right, so consider the function cosine of 1 over x squared. And we know that, right, so cosine function is bounded between -1 and 1. Because of the amplitude of this particular function. So again, cosine 1 over x squared is bounded between -1 and 1. The next step is to mimic the functions that given to us here, x to the 4 times cosine of 1 over x squared. Now, x to the 4th power, right, is the non-negative function. So therefore, when you multiply for all the term in this inequality, the sign of the inequality will not change. So what I'm going to do next is to multiply it x to the 4 for all the terms in the inequality. So I have negative x to the 4 less than or equal to x to the 4 times cosine of 1 over x squared less than or equal to x to the 4th. Now I'm going to take the limit for every term in the inequality. That is limit of negative x to the 4 as x approaches 0 less than or equal to the limit of x to the 4 as times cosine of 1 over x squared as x approaches 0, and the limit of positive x to the 4 as x approaches 0. Now, by direct substitution, this limit is equal to 0. And the limit for the middle functions remain the same here. And the limit of this function x to the 4, again, by direct substitutions, also give you 0. Now, at this point, you conclude the problem by saying that by the quiz theorem, the limit of the function x to the 4th times cosine of 1 over x squared as x approaches 0 is equal to 0. By the quiz theorem, the limit of the function x to the 4th as cosine times cosine of 1 over x squared as x approaches 0 equal to 0. Right. So this is a kind of a proof, right? So therefore, you need the beginning and you need the conclusion and the particular theorem that you want to consider, right? So this is quite important. This line is quite important. So be careful when you do this problem in the actual exam. Please use this statement in the conclusion of the problem. Now, moving on to the last part of the practice exam, when you find the derivative using derivative rules. So this is where the problem get easier to do, right? If you know the basic differentiation rules or product rule and quotient rule. Right, so for this problem, you have the function x squared minus square root of x. As I mentioned earlier, when you see a square root of x or or root function, it's easier to turn that into a power function so that you can find the derivative function easier and faster. So I'm going to rewrite this square root of x as x to the power 1/2. So this is x squared minus x to the power 1/2, and the derivative of the function is 2x right, minus 1/2 times x to the power 1/2 minus 1, or this is 2x minus 1/2 times x to the negative 1/2. Now in the test, I will have more explicit hint that you don't want the answer to be with a negative exponent. So let's try to turn this into a positive exponent. So that is 2x minus 1 over 2 times 1 over x to the power 1/2. So x to the power 1/2 is square root of x. So that is 2x minus 1 over 2 square root of x. So that's the answer for problem A. Problem B, clearly it is the product of two functions. So I'm going to apply product rule to find the derivative of this function. So this is u, right? And this is v. So f prime of x is equal to u prime times v plus u times v prime, or 3x squared plus x prime times 7x minus 4 plus 3x squared plus x times 7x minus 4 prime. All right. So the derivative of this function is going to be 6x plus 1 times 7x minus 4 plus 3x squared plus x times the derivative of 7x minus 4, that is just 7. Okay, so that's product rule. Now for the last problem, you have a quotient, right? So this is u over v, right? So for quotient rule, you apply quotient rule here. It's easier to do so in that sense. So f prime of x is equal to u prime times v minus u times v prime over v squared. All right. So the problem becomes x plus 1 prime times x minus 1 minus x plus 1 times x minus 1 prime over v squared. Right, so in this case, v is equal to x minus 1. So x minus 1 square. So derivative of x plus 1 becomes 1, right? Because derivative of x is 1 and derivative of the constant 1 is equal to 0. So you just have 1 times x minus 1 minus x plus 1 times the derivative of x minus 1, which is also equal to 1, divided by x minus 1 square. Right. Now the numerator here is simple enough for us to simplify. So let's do that. So x minus 1 minus x minus 1 over x minus 1 square. Right. So you cancel out x, negative x, and you're left with negative 2 over x minus 1 square. All right. So that's it for the video. Again, in this video, we went over some concepts for exam 1 and also the practice exams. Please let me know if you have any questions. Thank you.